Hey class, got a question here, number 24. Let me begin with a kind of a broader definition here. We had this definition from in class called the potential. Actually, even goes further back, but let me just put an integral of E times the distance that we integrate the electric field. So if we integrate the electric field, we get the change in voltage. In fact, I can't resist because we said the work or the energy is the integral of the force and the distance. Maybe I'll put a dx to match it. And that's what we did way back in chapter 7, I believe it was energy. And then when we got into this semester and this chapter, this force became electrical force, so this energy became potential energy. Then if we divide it by Q, F divided by Q is the electric field, right? The meaning of the electric field is the force per unit charge. And then the energy per charge is the potential. So if you go from some initial position to some final position. And then the difference between work and energy was a negative sign. So let me not forget the negative sign. Well, this was part of the lecture, and so I better not get too bogged down into that because you can go back and look at that. But I did want to point out then that I did this integral twice. Once we did it for what we call a parallel plate. So if you have a bunch of negatives and a bunch of positives, you will get an electric field, which remember electric fields start on positives and go towards negatives like this. And so this would be the electric field. And we said if it was uniform, then you have some distance here. What's nice is when you do this integral, you just get E, and you can factor it out, and so you're just adding up distance, which is d, and not worrying too much about the sign. I'll just put absolute value. We would get a change in potential of ed, and so if we went from the positive to the negative, it would be a decrease in potential, and if we went from the negative to the positive, it would be an increase, but this was the main equation. And we did that one first. Then we did the integral again, and we said, let's do this integral, but this time let's do it for the electric field from a point charge. And so instead of going along some distance x, we'll go along some distance r, and that would be the change in potential. And what we got here was a kq over an r, because, again, this r would be upstairs. It would be r to the negative 2. When you do an integral, you add 1 to the exponent, and that's why you end up with a negative 1. You also then divide by that new exponent, which is a negative, which then cancels with that negative, and that's how we end up with this nice equation for a point charge, or we could even extend that out to a spherical charge. And that is perhaps really the meat of this question. This question just simply says a 0.5 centimeter diameter plastic sphere used in a static electricity demonstration has a uniform charge distribution of 40, so I'll trust they mean positive here, 40 picocoulombs on its surface. What is the potential near its surface? All right, so I guess technically when we derived this, we were talking about a point charge, but you can see it comes from integrating the electric field, and the electric field would still look the same, whether it, as long as we were outside of the charge, it would look the same. And so if you integrate and you start here and go out or something, you would still get this same equation. And so if that's bothering anybody, that's why I wanted to take a moment to say the same integral that we did for a point charge would be the same integral we would do for a sphere. And therefore, this same result would work for a sphere. So if that was bothering you, let me clarify that. So I can just plug right into this equation here, and so I can get a number. It says, what's the potential near it? So I'll go ahead and put Coulomb's constant, 9 times 10 to the 9th. And remember, the units for Coulomb's constant are Newton, and then meters squared over Coulomb squared. The charge, well, this is the 40, and pico is 10 to the pico minus 9. No, nano is 10 to the 9. Pico is 10 to the minus 12. Okay. Yeah. All right, 10 to the minus 12. All right, so there is the charge on it. And the distance away, and then I guess this would be the distance from the center, kind of going back to our derivation. So if we're right on the surface, we would be equal to the radius. Now, they don't directly give us the radius, but they do give us the diameter. So the diameter is 0.5 times 10 to the minus 2, because it's centimeters, and I'll cut it in half. So that'll be in units of meter, and this would be in units of coulombs. And so I'll get the number here in just a second, but let's examine the units just to be careful here. It looks like one of the downstairs coulombs cancels with the top, and one of the upstairs meters cancels that. And so what we're going to have is a Newton times a meter over a coulomb. And a Newton times a meter is a joule. So we got a joule over a coulomb, and a joule over a coulomb is what we mean by a volt. A volt is 1 joule for every 1 coulomb. All right, perfect, because we want it to be in volts because we are measuring potential. And so the quantity is potential, the unit is volts. All right, so now I can grab my calculator here and go 9 times 10 to the 9th times 40 times 10 to the negative 12. Then divided by, and I'll just do this, divide by 2 in my head, so this is 0.25 times 10 to the negative 2. And it looks like we're talking about 144 volts. All right, hope that was helpful.